Let us now look at light and refraction. So we've seen before that at the interface between two media, light will reflect, but it also refracts, and that means that a beam of light passes from one medium into another will bend. Now the way it bends depends on the index of refraction of the two different media. So the index of refraction, n, is defined as the ratio of the speed of light divided by the speed in that particular medium. So it's 3 times 10 to the 8th meters per second divided by something less than that. So that means that the index of refraction will be greater than 1. Snell's law tells us exactly how much the beams of light will bend. And let's draw this out. So let's say that we have the interface between medium 1 and medium 2. Let us say that we have an incident beam, and from the law of reflection we know that this beam will be reflected so that the angle of incidence will be equal to the angle of reflection. But now Snell's law says that the beam will also refract, so that if this is theta 1 and this is theta 2, we have n1, so the index of refraction of medium 1 sine theta 1, that angle, is equal to n2 sine theta 2, which is that angle. So that is what Snell's law tells us. Now, there are two situations. One in which n1 is greater than n2, and one where n1 is less than n2. So let's draw these things out. So let's have n1 less than n2, and this is n2. That's actually the situation we had before, where I'm only going to draw the refraction. So here is a perpendicular. I won't draw the reflected beam. So when n1 is less than n2, the beam bends closer to the perpendicular. So theta 2 is less than theta 1, and that is all due to math. That's how we know that theta 2 will be less than theta 1. But now if we have n1 greater than n2, and this is n2 over here, and we have an incident beam coming like this, let's draw the perpendicular here. So when n1 is greater than n2, the beam will bend away from the perpendicular to the interface. So if this is theta 1, theta 2 will be larger than theta 1. So that's where total internal reflection comes in. So here let's say that we have an interface between two different media. This has index of refraction n1, the other one has index of refraction n2, and what's very important here is that medium 1 has a higher index of refraction than medium 2, and then if a beam is going to strike the interface between these two media at a certain angle, I guess I can draw here the perpendicular at this point, that beam will be refracted away from the perpendicular to the interface. This angle will be smaller than that angle, and I'm going to call them something. So let me put an arrow on this. This will be angle theta 1, this will be angle theta 2, and theta 2 is larger than theta 1. Now if we have a different beam that has an angle of incidence that's higher than theta 1, it will refract even further away from the perpendicular to the interface. So this would be angle, let's call it theta 3, and this would be angle theta 4. Now if we have another beam that has an even larger angle, it will refract right along the interface. So that is what we call critical angle right here. So for an angle smaller than the critical angle, we still see refraction. For an angle that's going to be larger than the critical angle, we won't see refraction anymore. We're going to only see total internal reflection. So the angle that the refracted beam makes for a critical angle is 90 degrees. So the refracted angle here is 90 degrees. If I get another beam that's even, I should change the color. So if I get an angle that's higher than the critical angle, that beam will be totally internally reflected. So here is the incident and here is the reflected beam. Now let's calculate what this critical angle is. Remember that Snell's law says n1 sine theta 1 equals n2 sine theta 2. We called theta 1, so that's the angle that the incident beam makes with a perpendicular to the interface, and we call that theta critical. Then theta 2 is the angle that the refracted beam makes with a perpendicular to the interface, and that will be 90 degrees. So n1 sine theta critical equals n2 sine 90 degrees. Sine 90 is 1. So then the critical angle is the inverse sine of n2 over n1. For angles smaller than the critical angle, there will be refraction. For angles larger than the critical angle, there will be total internal reflection. Now, fiber optic cables are cables in which total internal reflection takes place. So they look like this. They have a little coating-like thing on the outside. It's called cladding. And when a beam of light comes in, it will reflect back and forth in here until it can exit the fiber optic cable. So in this situation, this light will travel so fast through here because no light will be refracted outside, so there will be no energy lost through the refraction. All of the light will just go back and forth through the cable, and it will travel at the speed of light, of course, so it will travel really fast. Fiber optic cables are used, among other things, in endoscopes in medicine. So here is the equation for the critical angle for total internal reflection. Then one very important application of refraction is lenses. So there are different types. The real lenses look like maybe this. So here is a lens, and they are made out of some clear material, or plastic or glass or something, and it has some index of refraction n. Then let's say that the curvature, the radius of curvature of this surface is r1. So let me find maybe the center of curvature. So this would be r1. And then the center of curvature of this other surface would be here, so then that would be r2. So if we want to find the focal length of this lens, then we would have to do 1 over the focal length equals index of refraction of the material minus 1 times 1 over the radius of curvature of the first surface of curvature minus 1 over the radius of curvature of the second surface of curvature. So that's how we would have to figure out the focal length. And this equation is called the lens maker's formula. Now, we will use thin lenses a lot more. And for thin lenses, just like with mirrors, the focal point will be halfway between the center of curvature and the lens itself, or the focal length will be radius over 2. So the two types of lenses we will look at are converging and diverging. With lenses, we have a different sign convention. And the way we remember the sign convention is distances are positive where we expect the beams of light to be. Because with mirrors, we expected the beams to reflect back onto the same side of the mirror. So we said that that side was a positive side. If for some reason the image was formed behind the mirror, that was a virtual image, so the distances behind the mirror were negative because we did not expect the beams to be there. But with lenses are clear things. So we expect the beams of light to start on one side of the lens and then pass all the way through and form an image on the other side. So the object distance is positive on, let's say, the left side of the lens, and the image distance is positive on the right side of the lens because we expect the light to go all the way through. So let's look at some lenses. Let's look at some ray diagrams. Here we have a converging lens. And since there are two curved surfaces, there will also be two focal points. Let's say that there is a focal point here and one there. And then, of course, the distance from here to there has to be equal to the distance from here to there. And I guess I will extend my principal axis a little bit to the left here. Oops, there we go. So there would be the center of curvature here and a center of curvature on the other side. So this is one focal point, this is the other focal point, this is the center, one center and the other center. And I'm going to place an object over here. So we have to draw basically the same beams of light that we did with mirrors. So the first one is the one that comes parallel to the principal axis until it gets to the center of the lens, and it refracts through the focal point for the first surface. So this focal point is for that curved surface. So let me draw arrows on my beams. So this is the incident beam and this is the refracted beam. Then the second beam of light is the one that starts from the object, goes through the focal point for the second surface. And my beam is a little bit, let me redo that. So how about like that? So you see here that I had to go past the lens, and that's not a big problem. Just make sure that you always draw the line all the way to the center of the lens. All right, and then so the light that passes through the second focus will refract parallel to the principal axis. So it would go this way. And I'm going to draw an arrow on this as well. Now, the image will form at the intersection of the refracted beams, and I'm going to have to extend the green beam here. There we go. So that they actually intersect. So the image will be here. So that's image, that was object, and now the characteristics of this image are the image is inverted, it is larger by the looks of it than the object, and it's on the side of the lens that we expected a real image to form, so the image is real. All right, let's look at a different scenario. Let's say that we have another converging lens. So that's the principal axis. Let me draw the lens. Okay, so let's find us some focal points. So let's say that the focus is here. Oh, let me move it a little bit. So put the focus here, put another focal point over there. Make sure that in your drawing this distance and that distance are the same. Otherwise your images don't look very good. And let me place an object, and I'm going to put the object here. So the first beam is the one that comes parallel to the principal axis, like that, and it refracts through the focus through the first curved surface. I'm going to draw arrows on this. We have the incident beam and the refracted beam through the focus for the first curved surface. Now, the second beam will go from this focus through there, and I'm going to have to extend it all the way up to here. Let's see what we can do with that. Something like that. Let me just draw a line so that I'm absolutely sure that, yeah, that's good. All right, so that's basically the axis of my lens. And then I will have to draw a line that's parallel to the principal axis from here. So my beam of light refracts parallel to the principal axis. I'll put arrows on this. And so let's look at the beams again. They look a little bit strange because my lenses are a little bit too small. So we have the first beam coming in parallel to the principal axis, and it goes through the tip of my object. At the surface of the lens, it bends to go through the focus of this first curved surface. The second beam goes through the focus of the second curved surface, so that would be that point. It goes through the tip of the object, so it's a pretty steep line here, and then it bends, it refracts parallel to the principal axis. So if we look at the refracted beams, we notice that they will not intersect on the other side of the lens. So we have to extend these beams back, and I'm going to do it, this one first. So I extended it back, and I'm going to use dashed lines because the actual beams of light, the refracted beams, don't go on that side of the lens. And I'm going to extend this other one very poorly. So by my poor drawing, the refracted beams intersect at that point, which means that the image will be here. So what I can say about the image is that it's upright and it is larger and also virtual. We would expect a real image to form on the other side of the lens. So we have one more drawing to do, and that one is for a diverging lens. So there I have a principal axis, and now I'm going to draw a diverging lens. I have to draw my focal points. Here's a focal point, and there's a focal point. And the difference between the focal points for diverging lenses and converging lenses is that, I guess I'll color code them. This surface has a focal point over here. This surface has its focal point over there. If I look back at my converging lens, so I'll draw it up here. So converging lens, this surface has a focal point here. That surface has a focal point there. So comparing these two, so first curved surface has a focal point on the other side of the lens. Second curved surface has a focal point on the first side of the lens, on the left side of the lens, whereas with a diverging lens, we have the focal point of the first surface on the same side of the lens and the focal point of the second surface on its side of the lens. So that's going to change our drawings. So let's place an object somewhere. Let's say that we have an object here. So the first beam, again, is the one that comes in parallel to the principal axis, okay? And it refracts, so let's look at this beam. So that will refract through the focal point of the first curved surface. Well, here, the focal point of this curved surface is over there. So it doesn't reflect, but it refracts, so it will refract in that direction. So let's draw that, something like that. So I'm going to draw it, extend the beam backwards so we remember where that came from. And I'm going to put arrows on my incident and refracted beam. And then the second beam is the one that goes from the tip of the object through the focal point of the second curved surface. So the focal point of the second curved surface is over here. So the beam would have to start there, go through here, but at the lens surface it will bend parallel to the principal axis. So let us draw that. Something like this. And then parallel to the principal axis. So let me put arrows on this. That's the incident beam, that's the refracted beam. And we see that the refracted beams, these two, do not intersect on that side, so I'll have to extend them back. And the green one is already extended back, the blue one is not. So there I go, extending it back. And I also want to draw the dashed line for this just so we know which way the original incident beam was going. So the intersection of the refracted beams of this beam and that beam will be over here. So here is where the image forms. The image is upright. It is smaller than the object, and it is virtual. So again, an upright image through one lens is virtual. Upright image is virtual, whereas an inverted image is real. So let's look at the conventions again for the signs. The object distance is positive on the left side. So for all of my drawings here, the object distance was positive, DO. The image distance. So the image distance is this in this last drawing, and image distance is negative for this drawing. It's negative for that, but it's positive for this, because the image forms on the other side of the lens. Looking at focal lengths, the converging lens has a positive focal length, and the diverging lens has a negative focal length. All right, now another thing about lenses is that they have something we call a refractive power. And refractive power is 1 over the focal length. The refractive power is what doctors prescribe for our glasses. So if your glasses have a refractive power of -3 diopters, the -3 stands for negative is a negative focal length. So that's a diverging lens, and 3 is 1 over the focal length. The focal length has to be measured in meters for the refractive power to be measured in diopters. Now, if we have multiple lenses, we can attain that either by literally bunching up several different lenses, or we can have a lens here and another lens over here. So we have 2 different situations for lenses. The first one is touching, the second one is not touching. So when the lenses are in contact, their combined focal length is 1 over focal length 1 plus 1 over focal length 2 plus, and so on, as many lenses as we have, so that their power just adds. So with our eyes, for instance, there is the refractive power of our actual eye plus the refractive power of a contact lens that we can put on top of it. Now, if lenses are not in contact, then the image that's formed through the first lens becomes the object for the second lens. So if we have a converging lens, and here is an object, and those are the focal points. So let's say that the image forms somewhere here, like that. And then we have a second lens. Then the image to the first lens becomes the object for the second lens, and those are the two different focal points. So I'm going to draw a line that's parallel, and it goes this way, it refracts in that direction, and then the other line that starts towards that focal point will refract parallel to the principal axis, so the image will be formed, the final image will be here. So that's how we have a combination of lenses, and the image from the first lens becomes the object for the second lens, and then this would be the final image of the combination. The magnification for the combination of lenses is magnification of lens 1 times magnification of lens 2 times the magnification of lens 3, or however many lenses we have. Now, another concept is that of dispersion. When light passes through a medium, different wavelengths of that light travel at different speeds. And then when those wavelengths of light separate from one another, that's what we call dispersion. So an example of that is when light passes through a prism, or when it passes through a raindrop or a multitude of raindrops and form a rainbow.